All right. Well, last time we found the uploaded the outgoing connection and the file they downloaded to deface the server, and they got it from a domain name called with an IP address starting with 23. And I said it wasn't worth doing this one, but I found it is possible. It just the characteristics of Google search engine, it went up and down in popularity. So I just put the link here. There are people that record at malicious IP addresses and the history of how they've been used. And one of them is Alien Vault. And this one works. It shows you this is Wayne Corp, but we also used to be poisonivy.com. And this is useful information because criminals get a server and then they use it for one campaign, and then they use it for another campaign and another. So just going to an IP address that's done something bad and looking what else it's been doing will often help you connect attacks together and find other attacks. So um, finding other domain names that are there is useful. And the next thing to go is a brute force attack. And here you really see another great thing about Splunk. So first we're going to find login events, and those are typically post events with HTTP. So let's go back here. And right now I left this thing doing HTTP from a certain source. So I'm just going to get rid of that and do HTTP entirely. And for the moment, it'd be fine to have sampling. 1 in 100 would be good enough. So I have some events because now I'm going to find the method. The HTTP method is here, and that's either post or get, and I want the posts. So here's the posts. I have 176, and I'm expecting to find 15,000, but that's when I turn off the filter. So let's try that. If I turn off the filter and have no sampling, then I should get that number, 15,570. And I do. Okay. Now I want to exclude the attack traffic from the vulnerability scanner because that was a different attack. I'm not interested in that one right now. So to get rid of it, the simplest way I know is to just do the same thing you do in Google, go not Acunetics. That will just make sure this word does not appear anywhere in the event. So that should narrow it down to a small number, 441 events. Now, to look at the form data of these events, it's useful to make a table, and this is how you make a table in Splunk, pipe table, and then you list the fields. The underscore time is an automatically generated field, which is the time of the event, and the form data is the data sent as part of the HTTP GET request. And you see the first few have nothing there. These have what look like ordinary queries looking for things. But if you go further down in the list, you'll see a brute force attack. Username equals admin, password equals heaven, username is admin, password is bitches, and so on. This is trying, username is always admin, and it's trying a whole series of passwords. So I'd like to get just the brute force attack and not any of those extra things. So this is a phrase I'm only going to see in real attack traffic, username equals admin. So I'm just going to add that to my query in quotes. So I have to have that exact phrase somewhere in the event. And that should cut it down to 413 events, and they should all be part of the brute force attack. And now if I sort by time, I can just click the header, and this puts the 21.2, 21.24. Okay, this puts, so you see, here it is running 21.2 seconds, 0.2526. This is running many guesses per second, like looks like 50 guesses per second, really fast, going through a whole list of passwords, 1, 2, 3, 4, 5, 6, 7, 8, let me in, QWERTY, and just many passwords. So this goes on for a long time. And then if I go to the other end of it to see the end of the attack, I have, I'm not at the end yet. Okay, now I think I'm at the end. Yep, because what happens is, see, here they are, many guesses per second, 50.87, 51.1, 51.1, 51.3, many, many guesses per second. Then there's a gap of about a minute and a half here. and then another login, and this login has a different structure. Username equals admin. Instead of having the password over here, the password is right there. So what happened here is we had an automated script making many guesses per second, and that was the total number of entries here is 413. There were 412 guesses with different passwords, and then it found the right password and told the hacker, and the hacker logged in from a real browser. And another way to see this is to go back and look at the you can see a table here. You can watch the actual passage of it. So you can answer several questions here about the password. They want to know what was the first brute force password used, and you can find it. What was the correct password? You can tell because that's the password used by the attacker when they logged in later. And you can find the time interval between the time it found the correct password and the compromised login. That was that time at the bottom that's about a minute and a half. You can find the number of passwords that were used. All those are available from that list. And another interesting way to view it is to not use a table, but just view the events here. And then you can look at, say, the HTTP user agent. And you see 412 of them were a Python script running. And the one that came in later was an actual Mozilla browser. So this is the script running until it finds the password. And a minute and a half later, the attacker comes in. And these even came in from different IP addresses. If I get the source IP address, the Python script was run from this 23, but the attacker manually logged in from this address at 40. So you can see what's going on. They started some kind of scanner from one of their attack boxes, and then they logged in from another box they were using interactively. So you can have the whole, and see the point here, what we did before was find some outgoing traffic that downloaded a image and defaced the web page, which is probably the original incident that caused people to know something was wrong here. And now we're trying to figure out how that happened. And here we see they managed to log in as an admin into the content delivery system, which is, I think, Drupal or something. You'll find it somewhere in this request, Joomla. So they managed to brute force the administrator password for Joomla, and then they'll be able to put that defacing image on the web page, and they'll also be able to download malware and run it. And that's what we want to find. There was an uploaded executable file uploaded to the server as well. So we can do the HTTP events post without the vulnerability scanner and just look for executable files that were sent this way, because once they've logged in as administrator, they could then upload files. So here I want post and not this, and then I want just .exe to see executable files. And there are only two such events. And you can see down here, this is some kind of directory. And this is an actual binary file going by. And you can find the file name of this thing somewhere in this mess. There it is. It's 3791.exe is the file name of this thing being downloaded. And this is quite common. If you've done pen testing, there are databases of known exploit files for different vulnerabilities, and you run a vulnerability scanner. It says you have this vulnerability. Then you go to a database of attack files, and they typically have names like this, just a series of numbers, and you download the file there, which when run on this server will exploit that vulnerability. So that's the executable they ran, and that's another thing to take a note of for future use. All right. And we want to find that file's MD5 hash. And this is why I said sysmon is wonderful, because it gives you useful information. If you take a look at how sysmon works, sysmon creates log entries, but there's really only about 12 types. It's very simple, like all Rusinovich's tools. It's brilliant and simple. So you run sysmon, here you go. 1 is process creation, 3 is network connection, process access, and so on. Here, I think all we care about is process creation. They're going to download that executable and they're going to run it. So we want to see the process creation events when they ran it. So we're going to examine sysmon for process creation and look at the command line. So let's just go to the default search page and the data summary, because we saw it before. The sysmon data is here. So there's the sysmon events. Now, I got to go back. I'm going to turn on some sampling to make it faster and then show all time. Okay, so now I have some Sysmon events, and somewhere down here is going to be the event ID. And it's a small number, and I know the event ID 1 are the ones that are process creation. That's what I want. So now I'm down to just a small number of events. I can turn off the sampling. And now I think I want to find ones that look at command line. All right. Um, let's take a look and see what command line is available. And it contains the name of the program that was being executed. So I could just look through these and find it. I could probably just add the name of the executable just right here in the query too to narrow it down. Um, that was 3791.exe. So there are 5 events involved in executing that file, creating a process. And if I expand this to lay it out a little better, I see hashes here. And if you look at the available hashes, there are only 3 possible values of hash here. So I could just try them until I see which one is right. And the point is, it's a little confusing in Windows. In fact, let's just look at the command line here. Let's do a pipe table of, say, time and command line. That'll get us just the interesting data to look at. All right. And so you'll see this opens a command prompt. This executes that program. This does conhost. This does something else. So both of these have to do with running it. This, I think, is the one that runs the environment to run it in. This is actually running command.exe. This is actually running it. So that's probably it. If I add hashes to this, I think it was just called hashes. Yeah, then I can see. So I think the short one is the MD5. So anyway, you can track down the hash here and find that value. And that's the kind of thing you don't get in a normal Windows event log. That's one of the great things about Sysmon. You get hashes of executables because you're going to need that. All right. And so there's a bunch of flags to find there. And the last one is a ransomware attack, which is pretty awesome. So they determined that this host We105 desk, this is the desktop that was the origin of a ransomware attack. And so we're going to start by just finding events that refer to that host. And there's going to be a bunch of them. Now we're trying to find the IP address of that host. So if we look at the source field, um, let's see what source we have here. Okay. I think here's source. Okay. So there's various types of events that have that name in it, and the ones that are most interesting to us are LDAP. Those are Windows logon events, Lightweight Directory Access Protocol. So those would come from the server to this desktop, would be the IP address there. And so there's 74 logon events or LDAP events going on here. And if I look at the source IP, they all come from this IP address ending in 100, and the destination is this address ending in 20. And as you probably know, as a general convention, workstations typically start numbering at 100, and servers typically have low numbers, like 10 or 20. So this is probably the Active Directory server, the domain controller, handling the login, and that other number ending in 100 is likely to be the IP address of that endpoint. So that's another thing to save. This is the We8105 endpoint desktop. That's the IP of the desktop that was involved in this attack. And so now we're going to look at the suricata signatures that detected the server malware, because ransomware is not subtle. The original attack might be subtle, but when it's done, it just pops up a ransom note with the name of the ransomware. It's very obvious. So the um, intrusion detection system did detect it and called it server. So if I just search for the word server, I find a bunch of events, but I want to see the source field, which is going to give me 4 values. And I want these suricata ones, not these other ones. And there's only 5 such events. So suricata, the intrusion detection system, detected server 5 times. And then you can find the signature ID that alerted the smallest number of times. Even though there are 5 events, there are only 3 signature IDs, 2, 2, and 1. You can see them here. So that's how you find the flag. And the next thing, of course, is to see what the actual events were. Um, and so um, here is kind of a tricky one. I want to find, but let's see if I think I should be able to learn a little bit more about this. Alert signature. There we are. So this is check-in, domain lookup, and check-in. So I think if I do this, this is alert signature. Let's just make a table of this. It's easier to see. If I pipe this for table of time and that field, then we can see the time profile of the ransomware attack here. So here you go. If I sort by time to put these in order, now they're going forward in time. So at 9:49, server checked in. At 9:49, there was a response and another 9:49. So right within a few seconds here, the ransomware started. Now it started encrypting files. It kept encrypting files for about half an hour. And at 10:15, it was done encrypting files. And now it did an onion domain lookup to show the ransomware page. So you can see the time profile of how it happened. This is when the infection happened. This is the encryption. And this is showing the ransomware at this time. Now, I want to know the domain it looked up to find the ransomware page. So I want to look at DNS events very close to this time. That turned out to be the easiest way to find it. And the easiest way to do it is to just click one of these times. And that will narrow to this time range. And it went from 10:15, 6:68 to 6:69, so just a millisecond or something. And those are the events. Now, I think there's a way to get the time within a certain period here, which I could do a little better, but it's not bad. Uh, let's look up here. All right, let me get rid of the table here. See if it'll work this way. I don't want that exact range. I'm going to go back to all times. Oh, I could do it here. Okay, we'll just do it this way. I just want to be a really narrow range around here. So I'm going to go 10, 15, say 11 to 10, 15, 13. There. And I got to fill it in 0.00. There's one way to do it. There's a lot of ways to do it. But now I'm going to be looking at just a 2-second time period near when it looked up that event. And now I want to go back and look at DNS events here. So I don't need the word server, and I don't need that source. Just want everything in that time range. And I think maybe I need to put in a star or something to get it to search. There we are. So now I have thousands of events in that 2-second period. But if I look at the source, here's the DNS ones, and there were only 16 DNS events in that time period. So if I look at them, now I can look at the DNS query, which will be query here, there. And now I can see innocent domains like Microsoft and Bing, and this one that contains the word server. So this is the domain that led behind a Tor address and ultimately loaded the ransomware note. So that's how you can do it. One thing I should warn you is that Splunk works in your local time zone. So when I taught this class in like Illinois, people were trying to type in the time and they were off by an hour or two. That's why working from an event and clicking on the event and adjusting the time from that is the best way to make sure you actually get the desired time range, which is a problem in all incident response in large networks, is how you deal with time zones. So the next thing is, what was the suspicious domain visited by that desk on this date? So we can look at Suricata events on 24 August 2016. So let's just clear everything. Oh, I have Suricata already here. That's good. So here's Suricata, and all I need to do is restrict the time. So let's go from here to date and time range, and I want to go between 8, uh, 24 August 2016, 8, 24, 2016, and 8. I think I'll just put in 825. That should work, I guess. 2016. Seems like that would pretty much do it. Let's try that. Date range, date and time range. Apply. Okay, there we are. And I have 0 events. So let me see. Find Suricata events on that day. These are, well, let's just try no filter on this and then look for what type of events there are. Oh, I went from 824 to 825. All right. Somehow I've got an extra criteria. Probably I fouled up the time range. Let me go to clean search and let's start this way. Suricata was down at the bottom. I got to shrink my font. Somehow I can't scroll to the bottom. Okay, Suricata. There we go. And now all time. And here's another way you can use this time bar to specify time. So here's August 24. Uh, here's more August 11th. And here's August 24 to August 25, 7 a.m. That looks pretty good. If I click that bar, double click there, that narrows it to that range. Gets me pretty close to what I want. $86,579. Okay, there they are. Those are the events. Now, I want to look to source IP, and that has to be the web desktop. So that's source IP here. And the IP address I made a note of earlier was 192.168, ending in 100. This one here. So I want only that source IP. Those are the Suricata events from that desktop on that day. Then I want event type that loads web pages. And so that's HTTP. Now we're getting down to 38 events. We're narrowing it down. And now we can look at the host names to see what host names are visited on that day. And there they are. And again, there's a bunch of obviously innocent ones. And then an IP address. I'm not sure what to make of that. But here's the nasty one, solidarityproximity.org. That's the malicious one. And you can find that out by, for example, Googling it, I think, to find out what it is. Let's try that for completeness. If I go to Google and I Google solidarityproximity.org, then server ransomware. This is one of the domains known to be associated with the server ransomware. So that's the malicious domain that was visited by the ransomware. And now we can find the VB script. So we look for VBS and EXE, and we can find the actual script that was run to infect these machines. So I could leave this time restriction in there because it did have it at this time, .vbs and .exe, both in the same event. And I have 10 such events. And if I look at the body field, I may find the malicious one here, or I may have to widen up the time. Let's see. Nope, here it is. There's the script. You can see it right there. And well, there's the name of the script, my files. Here's the script, nsub. Yep, this is the one that contains all that malicious stuff. So if I go down here, in fact, might be good to make another one of those tables. Let's pipe table time, and body. Might be an easy way to see it. There. And this is a description of something, and that's a description. And this is the actual script. CMD set. Here's the script with a random name, and then it's got a for loop, subroutine, and these long convoluted names for things. This is the malicious script. And there are various questions that ask you about the length of that script and so on. So you can just see how it worked. And you can even find the specific USB key that was plugged in to start the infection and the number of PDFs that were encrypted and text files that were encrypted and so on. So you really learn a lot um, playing with Splunk. And that's what I wanted to show you.